All right, thanks for the introduction. So it's a pleasure to be doing mathematics virtually. I think we're lucky that our discipline and our style of life isn't hindered as much as for lots of other people. So you can see in my title that I've got a number of buzzwords of kind of physics style buzzwords: variational, Hamiltonian, symplectic, and I want to kind of just jump right into how these all tie together and trying to understand optimization. Now, I'm driven to study these things because I have a big agenda in mind, which is computation meets statistics. Inferential ideas go back hundreds of years. Computational ideas maybe a little less, and the blend of them, to me, it frames the biggest problems of our era. We want trade-offs between statistical inference and computation, and I don't think we have that yet. At least, certainly from a mathematical point of view, we have ad hoc trade-offs. But we'd really like to be able to say a priori, I'm going to solve a computational problem, and the error bars or the error in a hypothesis test is going to go down at some rate. And after some finite amount of time, I can stop and guarantee something statistically. The COVID is a great example of this. We need to make decisions as a society in a very, very timely way so that things don't get out of control. But these decisions are all based on data analysis and complicated computation, and they have error bars on them. And we need to know what those are and then know how long to run before we make the decisions. So anyway, that's the bigger perspective. Where do you get your ideas mathematically to kind of work on problems like this? Well, we need lower bounds, we need upper bounds, we need a model of computation. And I don't think that computer science is really providing that. I think that especially the lower bounds in computer science are too low. The model of computation is too broad. It's the Turing machine or related machines that can sort of do everything. And so optimization has stepped in to provide not just algorithms that we use all the time, especially gradient-based, but also lower bounds and oracles of various kinds that are not solving all possible problems, but are solving a limited subset so that there's viable lower bounds. And that gives us guides for how to design algorithms that actually try to meet those lower bounds. Now, on the other hand, there's brand new problems emerging that optimization hasn't faced before, especially with large-scale problems, millions of terms, sampling issues, especially non-convexity, and so on. So these are the kind of problems I've been working on for several years now, and I want to tell you about some of the progress we've made recently, especially by going into continuous time. So especially if you're trying to put lower bounds and upper bounds into register, continuous time turns out it's a discovery, really, has been out extremely effective and useful way to go. Just briefly, the algorithmic focus, when we talk about actual algorithms, not lower bounds, but algorithms and upper bounds, we are focused on gradient-based methods just because at the large scale we're at, that's really all that's viable. We're focused on stochastics because we're doing inference, and we also probably want to add extra randomness for kind of the usual reasons. And we're very interested in accelerated methods that'll get there as fast as possible. Like I talked about earlier, we want to be able to solve problems in timely ways so we make decisions quickly. Okay, so here's an outline of some of the things I want to say. And actually, I probably will only say something about the first three because the second bullet has become much more, we've done a lot of work recently on that, and I want to give you an update on recent progress on especially symplectic ideas on acceleration. Okay, so this was an early paper. There's basically two big ideas that have driven my group's work in recent years. One of them is going to come out in this saddle point paper where we're doing non-convex optimization, and we're going to be using probability ideas, in particular coupling techniques, to say things about non-convex optimization. So that's kind of maybe a surprising connection, and it's turned out to be extremely useful. Most of the papers we've done after that have had some kind of a coupling argument at the core. So with Chijan, Pranith, Netrapali, Rongu, and Shamkakad, we started this work about 3 years ago. And I want to just kind of briefly tell you the story here. We're trying to solve non-convex problems in this line of work. As you probably have heard from lots of our speakers, the architectures like neural nets, in principle, have lots and lots of local minima, but a lot of the local minima seem to be all reasonably good if you're in some bounded region of some kind, maybe near the origin. So the problem that we used to think of was the big one of finding the global optimum is not the biggest problem. And what is the biggest problem? Well, often it's getting away from all the saddle points. So the landscape in high dimensions, hundreds of thousands, will be littered with saddle points, which may only have a small number of negative eigenvalues, which are escape directions. And so how do you find those directions in efficient ways and give guarantees that you'll be past all the saddle points in a finite amount of time? So there's a picture of a saddle point in 3 dimensions, but imagine this thing tilted in some arbitrary way in hundreds of thousands of dimensions. How do we find that direction of escape? In particular, we want to get results which are not just rates, but also have the dimension dependence explicit and no hidden constants. Because if we're hundreds of thousands of dimensions, those things could kill you if you have a bad dimension dependence. If it's exponential dimension dependence, you're not going to, no hope. But even if it's poly, you're going to have troubles when we scale it to that level. So what is the actual dimension dependence? So this was kind of some of the background of when we were doing this work. We knew kind of from Morse theory, translated into discrete time, that gradient descent will asymptotically avoid saddle points. But we also had counterexamples that shows that gradient descent will take exponential amount of time to escape saddle points. If you forget about the asymptotics, you do non-asymptotics. But then on the positive side, we knew that if you add stochasticity, you can escape saddle points in polynomial time. But polynomial, again, we didn't know whether it was d to the 45th or d to the third, and even d to the third would be hopeless in hundreds of thousands of dimensions. So we know that stochastic gradient works, at least from the optimization point of view, in these really large-scale problems. Can we prove a stronger theorem? So just a little notation here. Let's consider, in this case, unconstrained but non-convex optimization. I've written down gradient descent there. Here's a picture in the convex case where we know that we get convergence to a global minimum. And this is the key part, the number of iterations in this setting is independent of dimension. You can run gradient descent in infinite dimensions, and the number of steps you take is the same as in finite. Which is already a little bit of the explanation of why gradient descent is so important and so useful, so practical. All right, but we're going to be running a gradient descent in non-convex problems where we have all these saddle points and other kind of singularities that we'd like to avoid and hopefully find a good nearby local minimum. Okay, so here just is a list of some of the problems that have lots and lots of saddle points, but they only actually have one global minimum. They have no local minimum. So there's this is a little bit old. It continues on. This is not true of neural nets, but it is true of lots of problems that most of the problem is saddle points. So just kind of briefly, I want to go quickly. It's a little older work, but just kind of the usual setup is that we have a smooth function with a gradient Lipschitz. We have the definition of convergence classically, a la Nesterov and the long literature, is that we want to arrive at a first order stationary point where the gradient vanishes. And to get a rate, we put an epsilon ball around the vanishing gradient, and we'd like to be within that epsilon ball in a certain amount of time. How long does it take? Well, this is a classical theorem. The number of iterations is 1 over that the size of that ball, 1 over epsilon squared. In the numerator, there's a constant 2, there's a Lipschitz constant, and there's the initial distance to the optimum. There are no hidden constants here. This is the result. So it's finite time, it's non-asymptotic, and it's got all the dimension dependence explicit. In fact, there is no dimension dependence. You don't see a D in that formula. Okay, so this is kind of a beautiful result. It suggests that we're kind of done for that version of the problem. All right, now we're not interested in convex problems so much anymore. We're interested in non-convex problems. So how are we going to find a definition which works in some generality, but not full generality? Non-convex can be too broad. So we're going to want to avoid saddle points. So we define a notion of a second order stationary point, which is again where the gradient nearly vanishes. But moreover, the smallest eigenvalue of the Hessian is greater than or equal to 0. But again, we give ourselves a little bit of slop so we can get a rate. And we don't, that funny parameterization there is just a standard parameterization where we don't introduce any new constant. We just use the same epsilon before, and we have a Lipschitz constant. So just slightly negative. So if we can avoid epsilon second order stationary points, then we're going to hit the local minima. So is there a rate that we can get for an algorithm to avoid second order stationary points? So here's the algorithm we had analyzed in the first paper. We've analyzed this with other algorithms since that time. But we know we need a little bit of stochasticity. So in this case, we just added the simplest possible stochasticity. Periodically, once no more than, or sporadically, no more than once per capital T steps, we do gradient descent, but we added noise uniformly in a ball of size R. And R and T are, the theory tells you how to set them to get the results I'm about to show you. Okay, so here is an example of a result. PGD will converge. Surprisingly, even though this is a non-convex problem, the rate looks just basically the same as convex. The number of iterations goes as 1 over epsilon squared. There's a Lipschitz constant and initial distance in the numerator. The only difference is at tilde, where we traditionally hide the dimension dependence. But now I'm going to tell you the dimension dependence. It's polylogarithmic. It's logarithm to the 4th power of d. Okay, so it's not, we would have been shocked if it were dimension free. It's not, but it's not exponential and it's not even polynomial. It's actually all the way down to logarithm. Now, I don't believe that I think it's probably truly logarithmic, but the proof technique, we don't still have a logarithmic result. The proof technique supplies that 4. And I want to tell you briefly what that proof technique is. Again, it's coupling. So here's a little picture on the left of the neighborhood of a saddle point. So in that neighborhood, there's a region where the flow is mostly towards the saddle point in that green region. So if you start in that green region, you mostly flow towards the saddle point, perhaps for a very long time in high dimensions, and eventually you're kicked out by the negative eigenvalue. Now that region is not a slab; it's kind of a curvilinear a pancake shape because the Hessian is varying in this region smoothly. So how do we get the width of that green region? That will tell us the rate, the dimension dependence. So we do it with probability theory. Imagine starting 2 coupled diffusions, both within the green region. They start to jitter around, and at some point, because they're both flowing towards the saddle point, they will couple. And so you can calculate or upper bound that coupling time. If the diffusions are a little bit further apart, one of them is outside the green region, it'll fly away because of the negative eigenvalue, and there will be no coupling. So you look for a phase transition in the coupling time in a probability argument, and that gives you an upper bound on this. That's what gives you this logarithmic or polylogarithmic result. Okay, so that technique of doing geometry by using probability theory here has informed most of the rest of our work. Okay, now that you get a very simple result like this, where there's no free constants and you look like you get it in dimension dependence, which is about as good as you're going to get, you ask, are we done? Can we characterize the fastest you could possibly go in this problem? And can we bring in ideas involving acceleration and stochastic models? Okay. So this is the second set of ideas that have driven our work. And now we're getting a little closer to the topic of this conference. So Hamiltonian ideas and symplectic in particular have driven this. So co-authors here are Andre Wibisono and Aisha Wilson, who are students with me, and Mike Betancourt has helped us a bit with some of the early symplectic work. All right, so this is a little bit of a almost facetious slide, but the fundamental theorem of calculus is, kind of one of the most powerful theorems out there. It relates differentiation and integration, and many fields that use mathematics at some point use both differentiation and integration and tie them together in complicated ways. So, physics certainly does that with Lagrangians and Hamiltonians. Being on the integration side, whereas differential equations, Newton's law and so on, are on the differentiation side, and then they relate them in deep ways. Statistics has its relationships, and the numerical disciplines do, finite elements, Monte Carlo. Optimization, really not. It's focused almost entirely on differentiation. You will pick up an optimization paper and see lots of gradients and Hessians and so on and so forth, and rarely will you see an integral. All right, so this line of work brings integrals kind of more fundamentally into the theory of optimization. So let's go again for simplicity back to unconstrained convex optimization. Here's gradient descent written slightly differently. And I'm going to add now a fact, which is that the convergence rate of this for smooth convex functions is 1 over k. That's an upper bound. So after k steps have gone by, you're guaranteed to be within a ball of size 1 over k of the optimum. All right. So it's a classical result. Now, knowing that result, and this was already known in the 70s, you might ask, is this the best you can do? You might, in other words, ask a complexity theoretic question. And what does that mean? Well, you have to have a kind of machine to talk about. So let's talk not about Turing machines. They're the best you could do would probably be to jump arbitrarily quickly. But let's talk about a machine that's only allowed to look at gradients and maybe all previous gradients it can store, and it's allowed to take steps in the linear span of all the gradients it's seen so far. So that's the Nemirovsky and Newton, one of the original Oracle models. In that Oracle model, they proved that the rate is 1 over k squared, that in principle you can go faster in the gradient world than just steepest descent, which is somewhat surprising. And then Nesterov came along and actually found an algorithm which has a rate of 1 over k squared. So this is the famous Nesterov acceleration. It is 2 equations. It's second order, not first order. The first equation looks like gradient descent, and the other one looks like a rotation of some kind. So this is a beautiful algorithm. There's a whole proof technology. You can extend it to lots of fields or lots of other problems in optimization. But it's still a bit of a mystery, so why is there a rotation here? Why is it second order? Is that needed? Why does this work? So our argument's going to be that you need to go into continuous time to start to understand this. Now, why? Well, in discrete time, what does it mean to accelerate? You're hopping along a set of points discretely, and acceleration would somehow mean hopping along those set of points faster. And that doesn't make any sense. You need a topology that supports the idea of going faster. So you need an underlying continuum in some sense. So let's go directly and embrace the continuous perspective and see if we can start to talk about rates. We want to get rates in continuous time, and we also want to have a variational perspective. We want to answer the question, what's the fastest you can go? Is there a procedure which is the fastest way to optimize? Is there an optimal way to optimize? All right. So this acceleration phenomenon is going to kind of guide us. These are these class of methods, which are not descent methods, but they're somehow faster. All right, so here's, let's just start our continuous time saga here with gradient flow. So gradient descent, if you take the step size to 0, you get out differential equation gradient flow. It has a rate, which is 1 over t. Sue Boyd and Candes had a very nice paper in 2014, taking the step size of Nesterov's method, that second order pair of equations, to 0, and out pops this ODE here. You can see a damping term, and it's second order, as it had to be. You can't solve this, but you can use Bessel functions and analyze it a bit. But there's still a mystery. Where did this differential equation come from? Why is it the right differential equation? Is it the fastest differential equation? Where's that mysterious 3 coming from? And so on and so forth. Okay, so with Andre and Aisha, we spent some time trying to develop a variational perspective on this, and we did. And this will be brief, but let me just sort of show you that we wrote down a Lagrangian. It's a time-varying Lagrangian. The alphas, betas, and gammas are not the important parts here. They're just degrees of freedom that give you a space of algorithms. They're diffeomorphisms. Really the important part is that Bregman divergence in the middle there, d sub h, so it depends on an auxiliary function h. It compares where you are, x, and where you're going towards, x plus time scaled x dot. So it's kind of elasticity. And then you subtract off the function you're trying to go downhill on, f, kind of like a potential. In fact, if h is quadratic here in the Bregman divergence, the first term reduces to 1/2 x dot squared. So this is really a literal classical Lagrangian. Now it's time varying. Nonetheless, you can do calculus of variations on this thing and minimize over curves, write down Euler-Lagrange equations as necessary conditions, and get out a ODE. So that the bottom of the page is our ODE. It comes from this Lagrangian. It is second order. It's very general. I don't know of many accelerated methods in continuous time that aren't within this equation somewhere. So the Sue Boyd and Candes in particular, if alpha is set to logarithm of t, this thing will reduce, and if h is quadratic, this will collapse all the way back to that equation. Now, there's lots of interesting mathematics that start to happen at this point. First of all, this is a covariant Lagrangian. That means no matter what rate you request out of this, you will follow the same path in the phase space. Okay, That's interesting. It means that the geometry is actually related to optimal way to optimize. It's not the actual speed. So if we ask for whatever rate we want, we'll move along the same path, but at different speeds. So in some ways, the phenomenon has kind of disappeared in continuous time, but we did recover the notion that the geometry matters. And we have a way to characterize the geometry that gives us the fastest paths. And now the new question becomes, how do you go from continuous time, where you figured out the right path, back to discrete time, where we know we have these oracle lower bounds and we can't do certain things. So it must be that you cannot discretize these differential equations at certain rates. So that's a kind of interesting complexity theoretic notion, that there's a discretization issue here behind acceleration, the geometry, how it relates to discretization. So here is a theorem which showed you the general rate. It's e to the minus beta t. Beta is this degree of freedom, which you're free to set. So you can actually have you can have an arbitrarily fast rate in continuous time. We have a Lyapunov function argument, which just kind of nails the convergence rate issue once and for all. But again, the problem is that when the dynamics get too fast in continuous time, it must be you cannot discretize the system of ODEs. So what happens, and can we identify that phase transition? And if it's possible to discretize, how do we discretize? So these are only phenomena that can be studied in continuous time. The notion of this phase transition doesn't exist in discrete time. So this, to me, is kind of one of the main motivations for why we have to move from discrete time algorithms into this embedded continuous space. All right, so I had learned about symplectic integration when I was a young faculty member back at MIT taking classes. If you haven't heard about it, it's a 100-year-old topic. Jacobi, Hamilton, Poincaré, and others worked on it. They already had in mind the problem of discretizing differential equations, but they had differential equations coming from physics, where there were conservation laws, energy, momentum, volumes, and phase space. And they were asking, if I have a discretization of an ODE, is it still possible that as I hop along my discretization, I still exactly conserve momentum or energy or other volumes of phase space? So that's a fascinating question. It says, can I still do the correct physics, but do it in discrete time? And they found a way to do that. And just kind of briefly, the idea is that when you're discretizing a flow, the classical way is to think of a vector field. You're at a point, you follow the vector a little ways, and then you keep doing that. The way these folks thought about it was to think of a triple of vectors at every point. That defines a volume, a small volume. As you move along the flow, that little volume will shear, but you'd like the volume to stay constant. The volume is a determinant, so you have a little bit of a polynomial constraint on your flow. And they were able to write that down as a literal constraint and find discretization methods that kept those constraints constant. Now, why do you do this? Well, first of all, you want to conserve these things. But secondly, when you conserve these things, new mathematics happens such the overall system becomes quite stable, even at very long time intervals. So you can now take much bigger discretization steps than you could otherwise with Runge-Kutta or whatever. And that, to me, was the connection to acceleration. We want to be able to take the biggest steps in discretizations to get downhill as quickly as possible. Just classical discretization didn't think so much about that, whereas symplectic did. All right, so there was a little machinery that we had to kind of think about to do the discretization with a symplectic point of view. First of all, it's more natural to work with a Hamiltonian formalism. So we took the Lagrangian, did a Legendre transform, and turned it into a Hamiltonian. And then there's kind of a recipe for taking a Hamiltonian and developing a symplectic integrator. So we did that, and here's just an example of doing that for a particular high-dimensional optimization problem. You can see this thing is going downhill. It's going down a hill at the rate that we advertised, and it's oscillating. It goes up and down because it's developing momentum, and that helps you to go faster. If you compare this to Nesterov, this is on a different problem where there's a little bit of a faster tail at the end. It's just as fast as Nesterov and really looks basically the same. But in fact, it's faster than Nesterov, because if you turn up the step size, this whole curve will shift to the left. Symplectic will continue to go downhill. Nesterov goes unstable. So the symplectic integrator is able to, when there's high curvature, actually damping in a way that keeps that controls for that, and Nesterov is not. All right. So this is a couple of years ago, but this was still a mystery. This is just empirical results, and it was kind of hand wavy to say that symplectic is kind of needed. Um, we didn't have necessary or sufficient conditions or any characterization of problems where you needed symplectic integration. And we also had a problem, which is that we're using Hamiltonian ideas, which are usually used for conservative systems, but we're trying to go downhill. So we want to get rid of energy. We don't want to conserve energy. We don't want to oscillate around. So that we've been concerned about that, and we now have a new line of work where I want to tell you about, which we have made real progress on that question. Before I get to that, let me just briefly mention once we have these two ideas at hand, continuous variational or Hamiltonian perspectives and coupling, we're able to solve a whole bunch of other problems that have been open in optimization, non-convex, convex, but also stochastic, where we go to diffusions, Langevin diffusions, and other diffusions. So here's just one example with Chi and Praneeth, where we looked at acceleration in the non-convex world where we have saddle points. So we put the two ideas together. If you have a saddle point and you're arriving at the saddle point, is it good to have acceleration or is it bad? And there was arguments in the literature about this. You might argue that as you come down to the saddle point, you want to somehow accelerate past it and not even see it, maybe. Doesn't sound very convincing. Or you might argue that if you have acceleration, you'll go up the other side and you'll slosh back and forth and it'll slow you down to have acceleration. All right, so anyway, let me not get into details here, but this is the same kind of notation as before. We have the second order stationary point idea. So it's the same slide as before, really. We're going to analyze this accelerated gradient descent in non-convex setting using our Hamiltonian ideas. Here is the Hamiltonian that we use. It's actually a pretty simple one. It's a first integral. Again, I don't want to get into details here, just to say there was a natural Hamiltonian to study here. The algorithm we studied was just perturbed accelerated gradient descent. So it puts the two ideas together. There's a perturbation that happens sporadically, and there is Nesterov acceleration. Now, here's what I wanted to emphasize, which is that the Hamiltonian gives us an algorithm, but it also gives us an analysis procedure. And when we go to analyze this optimization algorithm, we piece it apart and analyze different parts of it, guided by the Hamiltonian. The terms in the Hamiltonian tell us what to analyze when and how to actually get an overall convergence rate. Okay, so that's interesting. Going to continuous time gives us a new way to analyze these procedures. This slide is a little busy, but I just want to highlight the result at the very top and not get into all the Lipschitz constants and everything. But you can see that the result shows that we get epsilon to the 7/4, not epsilon squared. So this is a faster rate. So we've proved that acceleration helps you in the non-convex world. You get past saddle points more quickly if you're accelerating than if you don't have acceleration. Okay, and this next section, I think for want of time, I'm going to skip, but I want to just briefly highlight the kind of result. The other kind of direction that one wants to go is to add stochastics, to do this with diffusions, maybe gradient-based diffusions. And so people have been studying this with overdamped diffusions, Langevin diffusion, where you just add a gradient and Brownian motion. But we've been looking at underdamped diffusions. Just briefly, there's an overdamped diffusion at the top of the slide there. Just add Brownian motion and have a gradient. There are convergence results for overdamped Langevin diffusion, starting with Dalalian. The rates are 1 over epsilon squared, but not 1. It's d over epsilon squared. So you now pay a dimension dependence that's bad. It's d. It's an ambient dimensionality. Kind of makes sense. If you're doing Brownian motion, you're going to sort of see all of the ambient dimensionality. So we then analyzed a underdamped form of Langevin diffusion. There it is. It's now 2 equations, not 1. So a second order. It's a little more oscillatory. It has Brownian motion in the velocity, not the position. So it's a little smoother. And we analyzed this. Again, the proof technique here was in continuous time, obviously, but also we did a coupling argument. And we had a reflection coupling set up here, and that was allowed us to get this dimension dependence I'm about ready to show you. So let me skip that slide. Here is the result in red there. The dimension dependence goes from 1 over epsilon squared to 1 over epsilon. That's pretty pleasant. But even more interestingly, the dimension dependence went from d to square root of d. So somehow this algorithm is no longer seeing all the ambient dimensions, at least in quite the same way. You go from d down to square root of d. So anyway, we've been working on that a lot more. That's a whole separate set of talks, but I want to now In the last part of my talk, return now to symplectic integration. This is joint work with Guilherme Franca and Rene Vidal and Johns Hopkins. We're going to be defining a class of dissipative symplectic integrators. Okay, so we're going to face this issue head on, that we're wanting to do integration with Hamiltonian kinds of ideas, but Hamiltonians are usually applied to conservative systems where you have oscillations, classical mechanics. And in optimization, you don't want to oscillate, you want to go downhill. So let's try to face that issue. So let's imagine we now have a dissipative Hamiltonian system. That's easy to define. It's just a time-varying Hamiltonian. We're going to put this on a smooth manifold, which we'll be calling M here. We're going to also have a cotangent bundle where we have a conjugate variable, a momentum variable P. And we imagine that on this bit of differential geometry, on this manifold, we've got a dynamical system given by that Hamiltonian that moves along trajectories that can be viewed as solving an optimization problem. If you run it for a certain amount of time, it'll get close to an optimum in continuous time. And let's suppose that we've done our differential geometry and our dynamical systems analyses. We've got stability, we've got convergence rates, and so on. We'd like to know, can you now take all that analysis and return to discrete time and preserve those rates? Is that possible? When is it possible? What do we need? What assumptions? Okay, as I've already said, we're used to Hamiltonian systems for conservative systems, independent of time, but in optimization we want dissipation. So a kind of related question, the one we already asked, is can we take optimization algorithms, can we turn them into dissipative Hamiltonian systems that still have analytical insight for the original algorithm? All right, so these two questions are related. Preserving convergence rates is some kind of an invariance, and invariances are one of the reasons you study Hamiltonian ideas in general. Okay, so we're going to approach this with symplectic geometry, not just symplectic integrators, but we're going to actually take a geometric perspective. We're going to show that symplectification, I'll describe what that is, plus a notion of gauge fixing. If you put those two together, you can talk now about dissipative Hamiltonian systems in a straightforward way. Then we're going to do backward error analysis. This is critical to show that you can actually still conserve rates from the symplectic world into this dissipative world. Okay, so a little bit of setup here. We're going to have a smooth manifold M, and we have a dynamical system defined on it, given by a vector field there, capital X. The notation is now going to be a little more differential geometric. So we're going to have a flow map, which is given by the exponential operator. And we're going to define a numerical map in the standard way. It's just going to be a map for an approximation step size h, which has a certain error between the flow, I guess that's phi, Greek phi, and or variant phi, and the true flow. The numerical flow, normal phi. All right, and these numerical maps have different orders of approximation, and we'll call that R. So it's known how to do this in a wide variety of problems. The names at the bottom of the page give you some of the numerical analysts who've worked on these things. And one of the theorems that they've been able to prove in this manifold world is that every numerical method can be thought of as an exact flow of a certain perturbed dynamical system. Okay, so there's an expansion of that gives you a perturbed dynamical system, and the numerical map is the exact flow of that perturbed system. So mathematically, that's a very advantageous perspective to take. All right, now we can also then start to get approximations and do backward error analysis if we truncate the perturbed vector field. All right, so let's now truncate it, do the expansion out to a certain level, and define the flow associated with the truncated map. And again, theory from the numerical analysis literature shows there exists a family of truncated perturbed vector fields such that the error term can be controlled exponentially. Okay. Now, for typical numerical integrators, we're not doing this truncation, so it's not clear why this is all, it's a nice piece of mathematics, but why is it so useful? But in our world, we're trying to find X tildes that aren't just truncations, that they preserve some structure. So they preserve maybe a symplectic structure. Then we want to be able to show that you have a small error, backwards error analysis. Okay. If we're going to use symplectic integrators, we want to be able to have this invariance property numerically. Okay, so just a little bit more notation. A symplectic manifold, and now in full generality, this is now symplectic geometry, not just symplectic integration, is defined on an even dimensional smooth manifold that has a non-degenerate two-form omega. Okay, so this is a skew symmetric object, and its existence imposes a special geometry on the manifold. Okay. And symplectic geometry, even though it's a 100-year-old field, it's still very active in mathematics departments, relates many other topics. All right, so now we bring in Hamiltonians, and they go together beautifully with symplectic manifolds. All right, so let's now talk about the tangent bundle of a differential manifold. Well, the tangent bundle is a symplectic manifold, so that's a theorem, and the symplectic two-form is associated with is just a wedge product between these coordinates, the momentum coordinates and the position coordinates. Okay. All right, so that already kind of gives us a connection between simplexicity and conservative Hamiltonians, and the related theorem is that the dynamical system preserves the symplectic structure, which might be a volume in phase space, it might be a momentum, it might be an energy, or other structure, two forms, if and only if it's a conservative Hamiltonian system. So now we've really tied together symplectic with Hamiltonian. So this is classical theory emerged over sort of 100 years, starting with Hamilton. And now to kind of bring that into real analytic expression, preserving literally means that something stays constant. And the thing that stays constant is a lead derivative of this Hamiltonian vector field. Okay. The second thing which stays constant is the actual overall Hamiltonian is conserved. Okay. So again, we're back in the conservative world where that happens. All right. So now we return to symplectic integration in this more general geometric perspective. And this literature, Harrer et al. And many others, have shown that there is a systematic way to construct symplectic integrators that conserve this form, that preserve these two forms, omega. Okay, these are the symplectic integrators in vast generality. Okay. Okay, so that means that you can do this truncation if they are symplectic. Then the perturbed dynamical system will also have a lead derivative which vanishes. Okay. Moreover, the energy will be constant. Okay, so this provides the backdrop for why symplectic integrators are so successful in practice, because if you now do the backward error analysis at this level of generality, you can show that the discrete system will have a continuous flow part of it, and it will have a bounded error. And the error bound is explicit, and the simulation time T sub L is if you plug in typical constants for all these values for the order H and for the step size 8, the order R, the step size H, these simulation times can be very large. And so you have a theory that says why symplectic integrators can allow you to take very big steps and still have a small error. So this is related to but different from the notion that you have a conservative system. Okay, so now we want to take these ideas and put them into the dissipative world. Okay. So the dissipative world, this breaks down. We don't have a Hamiltonian that we want to keep constant. We want to dissipate energy. So we want it to go to zero. Okay, so we want to nonetheless work with Hamiltonians. We just don't expect anymore that dH dt will be equal to zero. We also don't expect that the symplectic form will be preserved, that the lead derivative will be zero. Okay. All right, so you could naively try to apply symplectic integrators nonetheless, and that's kind of what we did in our early numerical work, and they may work, but we lost the mathematics. Okay, so this is the last part of the talk now. There's a paper on this, which I think I had on the title slide of this section. It's on the archive. We are going to define the notion of a presymplectic manifold. This is one that has a dimension which is 2n plus n bar, N bar for us is going to be equal just to 1. So this is now an odd dimensional manifold, okay? And it's going to have a 2 form, but the two form is not going to be of dimension 2n plus 1. That's not possible, but it is dimension 2n, okay? So it's a degenerate 2 form, okay? So when you can do this, you call this a presymplectic manifold. Okay, now we're going to do a notion of symplectification. We're going to embed this manifold into a 2n plus 2 manifold, a little bit bigger. We're going to have coordinates which include an explicit time variable and its conjugate variable, okay? So we build in energy conservation of this conservative system by just making sure that the new time variable s, derivative of this bigger system with respect to s, is equal to 0. Okay, so we've embedded our original presymplectic manifold into a higher dimensional conservative manifold. That alone is not enough to do the backward error analysis. We're going to need another idea, and this is the last idea. So we're going to also do something which is called in physics gauge fixing. We're going to set these extra degrees of freedom in a particular way so that this dissipative system lies on a particular hypersurface where you have a constant Hamiltonian. Okay, running out of time here, so I may not go through all the detailed notation here, but it's a straightforward embedding. It's a particular way of setting the extra degrees of freedom. Okay. So now we've set this up in such a way that if you look at the symplectic structure of the bigger system, the conservative system, you can recover the presymplectic structure of the dissipative system. Okay, you can go back and forth between the two. All right, so now we're going to define the notion of a presymplectic integrator, which is an integrator for a dissipative system, and it's just gotten by taking a reduction of the symplectic integrator for the symplectification. So you go up to the bigger world, you do a gauge fixing, you define a symplectic integrator there, and then you just express this in terms of the variables of your dissipative system. Okay. All right. So with all that set up, we can now do some theory. We can show that the decaying Hamiltonian now will be nearly preserved. The continuous to numerical map will have a small error which we can control in the same way as the symplectic integrators control these errors with a backward error analysis. Okay. All right. So we've applied this to a general class of Hamiltonians, and then I'll show you briefly the application of the Bregman Hamiltonian. So here is a class where we have separations. We have a time-varying piece, kind of a kinetic piece, a capital T, scaled in a particular way, and then we have a potential f of q, which is not time-varied, but then is scaled in a particular way. So let's call this separable. The second term has no momentum term. The momentum term is in the first one. In this case, we know how to do with Lyapunov theory rate analysis in continuous time, like I was saying earlier. And so in this case, we're actually able to apply the presymplectic theory that I just showed you. So we're able to show that the discrete rate is the same as the continuous rate if we're using a presymplectic integrator up to a small error. Okay, so that's exactly the kind of theory we wanted before. We've now been able to establish for this class of Hamiltonians. Okay, so the implications for optimization are that we can actually do this rate matching that we've been looking for a few years now. We have explicit results that depend on step size and on error. The step size can be quite on order. Step size can be quite large. The R is less important here. It's dominated by that exponential decaying term and the error bound. So use of high order integrators is not so important here as it is in the physics world. We can get by with very low integrator or low order integrators and still get the benefits of symplectic integrators. You can relate this to heavy ball damping and Nesterov's damping. These are particular choices of this eta1 in our notation. One of them is linear, the other is logarithmic, and you can consider other possible choices. Okay, so to finish up, let me just now apply this all the way back to the Bregman dynamics. The Bregman Hamiltonian is an example of that separable Hamiltonian we wrote down. So we can just apply with all this notation, we can apply it just in a straightforward way. We can now put the two parts of the talk together. So if you go back to the Bregman Hamiltonian, I wrote it again up here at the top of the page. We write down the Hamilton's equations here just by using Hamilton partial derivatives. And we had a rate result before, which I've now copied down again. It's e to the minus beta t. Okay. If in particular we choose the h of x to just to be a kind of classical kinetic energy with a mass matrix, the overall Hamiltonian simplifies as shown at the top of the page now. We can apply any presymplectic integrator or any symplectic integrator to the larger conservative system. So here's one that's based on the leapfrog method out of the symplectic literature. And that's just an explicit thing you can now put in MATLAB or your favorite language and go ahead and integrate this now dissipative system. Okay. In the non-separable case, it's also possible to make progress here. You can write down all this mathematics and you will get out a blend of explicit and implicit steps, which is fine. But the implicit steps, you'll probably have to do extra numerical work. But there is also a way to get this to be entirely explicit. And so it's done by a duplication of the degrees of freedom. This decouples things, and you can write down just kind of classical leapfrog type integrators, and there it looks kind of complicated, but it's very explicit. You can just put this literally as is in the computer to define your steps of this integrator. Okay. So you compose these maps in various ways. You get all kinds of integrators. In particular, we've written down the so-called Strang composition at the bottom of the page. Okay, so I've arrived at the end of the talk. This section, let me just summarize. We have introduced a notion of presymplectic integrators, which are appropriate, suitable for simulating dissipative Hamiltonian systems. So we've shown applications to optimization. There are also possibly other applications in many body theory and control theory and economics, where you're also trying to simulate dissipative systems, worth exploring. So we have done something which we'd hoped to do quite a while ago to show that symplectic ideas are relevant to optimization. They allow you to take big step sizes, and that allows you to make fast progress and get kind of these optimal accelerated algorithms. We've done the theory that shows how you can do rate matching. This is one way to do it. There could be other ways, but this is we finally got a way to do it. And we can now sort of do analysis in continuous time and discrete time jointly, going back and forth and getting the advantages of both worlds. Okay, so that's all I really wanted to do today. Just a few kind of comments about more future directions. We've been very interested in doing this for game theory. So where saddle points are not the enemy, they're your friend. You'd like to converge to saddle points. So are there fastest ways to converge to saddle points? Symplectic ideas turn out to be relevant there too. I've worked with a student, Eric Mazumdar, on that, showing that you don't like the symplectic component of the vector field. That gives you oscillations. You want to kill it, and you can actually converge to things like Nash equilibria quickly if you kill the symplectic component. Moreover than all the kind of world of stochastics, where we're doing this with Langevin, and then can we find also variational or Hamiltonian-like principles for the stochastic systems to try to bring these set of ideas over into that world as well. So we're kind of partially along in that agenda. So I'm going to finish there. Thank you for all of your attention, wherever you are. I enjoyed being able to give the talk. Thank you.